So there's another way we can think of calculating the delta H of a reaction. Remember, don't forget about enthalpy. Just because we're on a different chapter doesn't mean enthalpy goes away. And this way of calculating delta H is still, I'm going to write over here, it's still H final minus H initial, okay? But the way this ends up working, because of the fact that we have to supply energy to break bonds and that we get energy out when we form bonds, okay, this formula ends up becoming bonds broken minus bonds formed. Okay, so it's a pretty easy to remember. The sum, so right, sigma, that tells me the sum with all the number of moles times the energy of the bonds broken minus the sum of all of the energies of bonds formed. Okay, and as an example, here you can see this is the reaction, the combustion of methane. So let's write that down. Combustion of methane. All right. And we can see overall here when we start, this is my initial state right here. And this is my final state. And we can see it's exothermic as expected because it is a combustion reaction. However, we can start to see now why you have to spark a mixture, right? When you have a mixture of methane and oxygen, it doesn't necessarily spontaneously combust, though it could if we raised the temperature high enough. That's called the flash point. So we do have to put some energy in to get those bonds to start to break, right? Specifically, we have to break 4 carbon-hydrogen bonds and 2 oxygen-oxygen double bonds. And that gives us all of our available atoms, okay? As it turns out, the chemistry is a little bit more complex than that. But all the same, now when all of these bonds are formed, specifically 2 carbon-oxygen bonds and 4 oxygen-hydrogen bonds, that releases a ton of energy. And if we compare the energy in to the energy out, you can see overall, right, that gives us our delta H, our negative 808 kilojoule per mole. Okay, so let's go. I'm going to actually walk you through that, and let's do that as a sample calculation. Okay, so we're going to do the combustion of methane. Okay, so first let's get that reaction. CH4 plus O2 makes CO2 plus H2O. Additionally, when we do this way of calculating delta H, we have to get the right Lewis structures. Okay, so let's do that. We know that methane is all single bonds, and obviously, you know, I had it on the other page, right? But and then I didn't balance the reaction, did I? Okay, so 1 carbon and 1 carbon. Let's see, 4 hydrogens. Aha, I have to put a 2 right here to make 4 hydrogens. And then now I've got 4 oxygens, so I need a 2 right here to balance it. Okay. So as I was saying on that other slide, you saw all the Lewis structures. But you know, in a homework problem or in another calculation, you would first have to get the Lewis structures. So you get the balanced reaction, then get the Lewis structures. Okay. So hopefully you remember that oxygen has a double bond, okay, with 2 lone pairs on each oxygen. And of course, there's 2 of them, so I'm going to draw both of those oxygen molecules so I don't miscount my number of bonds. And let's see here, we're only forming 1 mole of CO2, okay, and we remember CO2 looks like this. And we're forming 2 moles of H2O, and oxygen is the central atom there with 2 lone pairs on oxygen, and we made 2 of them. Okay, great. So now we can count up all the number of bonds, and we can get the formula. Okay, we can get the calculation going. So delta H of reaction is, let's remind ourselves, bonds broken minus bonds formed. Okay, so my bonds broken, I'm going to have 4 carbon-hydrogen bonds, right? 1, 2, 3, 4. Okay, so let's do that. So we'll say 4 and then times, let's see, where is it? Here we go. CH it's 110 picometers and it's 413 kilojoules per mole. Okay, and so let me write down, let me put the unit in front of that 4 so we recognized, so 4 mole, right? The mole and the mole is going to cancel, okay? And now that's plus 2 oxygen-oxygen double bonds. So this is why we have to get the right Lewis structure, because here you can see on this chart, I've got an oxygen-oxygen single bond, but we really need the oxygen-oxygen double bond. So that's at 495. So I did it again, 2 moles. 2 moles times 495 kilojoules per mole. So that's the sum of my bonds broken minus my bonds formed. So there's only 1 carbon dioxide, but there's 2 carbon-oxygen double bonds in the carbon dioxide. Okay? So let's go and look at the list here. Carbon-oxygen. Oh, look, there's a little note next to carbon-oxygen. Aha. The bond energy of a carbon-oxygen bond in CO2 is 799. That's an exception. So make sure you notice that. This table doesn't have any other exceptions, but every now and again, you will see something like that in these tables because chemistry is the science of exceptions. You knew that. Okay, so there's now 2 moles of carbon-oxygen double bonds in CO2 at 799 kilojoules per mole. Okay, and then now that's plus 4 oxygen-hydrogen bonds, right? Each H2O has 2 moles of oxygen-hydrogen bonds, but we have 2 moles of H2O to give me 4 in total. So now an HO bond, there it is, 463 kilojoule per mole. And I just realized I have my periodic table up here, but really for this lecture, I needed my calculator. But if we were to go to do this, you should prove this to yourself. So luckily, the answer was already on the right page. So prove this to yourself that it works, okay? If we were to go through and calculate this whole thing, we would come up with that negative 808 kilojoules. So give that a shot, okay? Great. And